All right. Okay, should be live streaming. So welcome to this lecture. It's on December the 3rd, 2016. And Assalamu alaikum. Okay, so I'm just going to check my audio here once it comes on. Okay. Okay. Yeah, looks like it's okay. All right. Now I wanted to try out a new feature, and that was there's a scene here which I can switch to. I want to show a maple screen, so hopefully that will come on. We'll see this later. Okay, so we'll go back to that later. All right. So last time we were discussing polynomials and graphing polynomials. Okay, it looks like it came on. Good. And I was going to list all the features that it's good to at least look at or calculate when you're given a function which is a polynomial and you want to plot a graph. Okay, so I was doing examples of this. So one of the things that you would for example, you would do is find the roots or the x-intercepts. Okay, this is all in the textbook, Abrahamson, in section 5.3, around there anyway. How to sketch graphs of a given. So you find the one thing is to find the x-intercepts. So these would be also known as the real zeros or roots. We're taking the degree to be n. All right. And also the y-intercept. There's only one y-intercept whenever you have the graph of a polynomial, because it's a function. You have one intersection in the x along the y-axis here somewhere. One intercept. Okay, so you just set x equals 0, and that gives you the value for y. Number 2, we were doing this before, is you check the symmetry. So basically odd or even. Okay, and that you can do algebraically by seeing if there are if the powers of the polynomial are all odd when you've expanded it out, like this. So this would be an odd function, or whether they're all even, maybe like that. And the other possible, well, there's the other possibility, of course, there's no symmetry. In that case, you'll have a combination of both kinds of terms. All right. So then you can use, if you can find all the roots or write the polynomial in terms of a product of all the factors, of linear factors, those will give you all of the roots of the polynomial. And in particular, should be able to find out, in principle at least, whether the multiplicities are 1, 2, 3, or so on, what the multiplicities of each root are. So you'd use the multiplicities of each root once you get them. To determine the behavior at the x-intercepts. Okay, so if it's an odd multiplicity at that root, or at that 0, then the graph will bounce off of the x-axis, one way or the other. Okay. And if it's an odd multiplicity, so these are even multiplicities. If it's an odd multiplicity, then the factor will be multiplied by itself. It'll be raised to an odd power. And then you'll either have, if it's a 1, it will simply cross the x-axis. And if it's odd, it will cross the x-axis, but it will do a little, it'll go horizontal on the x-axis, one way or the other. Something like that. It's higher power, it varies more sharply right at the, near where it crosses the axis. Okay, so those are examples. I'm just showing different examples of polynomials in different regions there. And determine the end behavior. That will help you to. Oh, and I would say so I should mention here. You can at some point, let's call that 3. Let's call that 3A and 3B. If the 0 has multiplicity 1, then you'll be able to find the straight line and, well, approximately what the straight line is, where the graph will follow that through the endpoint, and you can find the slope of that straight line by doing what I showed you. So this is over and above what's in the book. Find the slope by evaluating the rest of the factors at that root. So just evaluate all the factors except a linear factor corresponding to this root. And that gives you the coefficient, which is the slope. Okay? So it's kind of like a little bit of calculus that I'm teaching you. It's showing you how to find. It's really the instantaneous slopes through the along the curve at the 0. But it's a very special case where you don't have to use all the methods of calculus to find the slope. You just find like we showed last time. You find the factor. Say this is -2. The root's there. And whatever it is outside, x plus 3 or whatever, you just evaluate that at x equals -2. So here we get 4 squared minus 1, 3 times 1 is 3. All right, so you get a slope of 3 there. All right, so it tells you whether the graph is going up or down through that point. So it's useful for determining what the graph looks like. All right, and similar things can be done for a root of multiplicity 2, like this. You can use that extra coefficient. You can evaluate that coefficient. If it's positive, then it's above the graph. If it's negative, it's below the graph. And similarly with any cube roots. All right, so determine the end behavior. Okay, so if all is well here, then all these behaviors through the roots and at the ends will be consistent with each other, and you'll have shapes like this, and it just becomes a matter of connecting the dots. You might have an intercept here on the y-axis, and then and behavior down like this. So the connection of the dots will provide you with a graph something like this maybe. So number 5, use the end behavior and the behavior of intercepts to sketch the graph. So that's what I'm doing here. So use 3 and 4, 3AB, and it's called 3AB and 4 to sketch. Okay, and then ensure that the number of turning points is consistent. So if it's, say, a graph of, say this is n equals 5, 1, 2, 3, 4, 5, yeah, so it has 5 roots. So the number of turning points should be at most 4. Let's see, 1, 2, 3, 4. That seems about right. So turning points, number of turning points should be n minus 1, which is 4, check, all right. And then you can always check it using a graphing calculator or other technology to check whether you've gotten the right thing, if that's available. I guess on a test or quiz it won't be available, so but here they suggest becoming familiar, if you can, with the graphing calculator or something like that. Maple maybe. Okay, calculate a few other points. Calculating a few other points using a regular calculator is also a good way of making sure what you're getting is a reasonably close answer to the right answer. Okay, so those are the main steps for using. So that's number of turning points is number 6, and number 7. Use technology. Maple, graphing calculator, and so on. At least a calculator would be helpful. It doesn't have to be graphing. That's quite a bit more expensive than a regular calculator, but just having a simple calculator to evaluate the y values at different values of x is really helpful. Okay. Now, the intermediate value theorem. I don't know if I discussed that before, but in case I didn't, I'll just review it quickly. Intermediate value theorem says that if you have a continuous function and all the polynomial functions are continuous, that means in order to draw the graph, you don't have to remove your pen from the page. Okay, so you might have something like this. And the intermediate value theorem concerns the behavior of a function in a transition area where the value of y transitions from a negative to a positive value or from a positive to a negative value. So here to here is positive to negative, here to here is negative to positive, as x increases. All right, so there's a transition region where it's going the other way. Okay, and the theorem says that if a value of x, say x equals a, gives you a value for the function that's less than 0, and there's a value of x greater than a, namely a b, so b is greater than a. Let's just write this in this order. Then fb is greater than 0, we know there. Let's suppose we know all this, okay? So we have the value of a, we can calculate the value of f there, and it's negative. And then a value of f, we can calculate that, and it's positive. Then the intermediate value theorem says that, let me write it down. if you have that and b is greater than a, then there's a c. There's a third point somewhere in the middle where the value of the function is 0. So there's a c such that a is less than c less than b, where f of c is just exactly 0. Okay, so this is one way to search for roots if you're having trouble finding them. So if we know the roots for a polynomial, that's very helpful in sketching the graph, right? And among other things too, we might need it for certain purposes, like to see where the domain of a polynomial should be in order to make sure the polynomial is always positive. Okay, so in physical situations, that's what we would, if we want physical values of y, sometimes y has to be positive, like the dimensions of the box, which give you a positive volume. Remember, we had that problem last time. So, but sometimes it's hard to calculate these roots, okay? But it might be easier to calculate points just below and above them. And the roots might have to be estimated. In fact, there's a way of sequentially, finding consecutive upper and lower bounds which squeeze in closer and closer to that root. And using a calculator, it makes it go quicker, and such that you can check that there's a sign change between the values of a and b as a and b come closer and closer together each time. And so that tells you that the root has to be contained within it. So you keep on raising the lower bound and lowering the upper bound, all the while keeping these conditions the same, and you can get closer and closer to a value for that root just by limiting the upper and lower bound, making them close enough to each other. Okay, so that's useful if you can. It enables you to be able to get a root, say up to 3 decimal places, or as many decimal places as you want. It just takes more time and work to get there. Okay. All right. So, but it's a process of guessing, and all right. So it just takes time. All right. So try number 4 was an example that I wanted to do for this one. That says. Given a polynomial, okay, let's just put this over here. Given a polynomial, it's f of x. I believe this is section 5.3. So try number 4, section 5.3. It says we're given this polynomial. F of x is equal to 7x to the 5th minus 9x to the 4th minus x squared. All right, so that might be a hard polynomial to factor. It's got high powers of x. So show that it has at least one real root between x equals 1 and x equals 2. Let's try a better pen here. Show that it has at least one real root between x1 and x2. Okay, so that's one thing I forgot to mention here. There might be more than one root, more than one point C for which this is true, but we're guaranteed there must be at least one. So I might put it this way: there is at least one value of c, because the graph could behave like this. It could go up and then down and up again before x equals b. So you might have this situation, or it could cross any odd number of times and still change sign from A to B. Okay, but this is all we need to find out, is there a real root at all between those 2 points? And so, well, you can set it up using synthetic division really easily here. You just write the row of coefficients in the top. So 5, 4, and then there's no 3, so that's a 0. 3, 2, minus 1. 0 for 1, and 0 for 0. Okay, so I evaluated x equals 1, and I get 7. Remember, I multiply this by 1 and add to this number. And then I get 7 times 1 is 7, minus 9 is minus 2, times 1 is minus 2, plus 0 is minus 2, times 1 is minus 2, plus minus 1 is minus 3, minus 3, minus 3. So I get zeros there. Okay, so it doesn't evaluate to be a root itself, because this is not 0. But let's see what happens when I put in x equals 2. It's negative here. So if I plug in 2, then I get 2 times 2, 7 times 2 is 14, minus 9 is 5, plus 5. 1 times 2 is 10, plus 0 is 10. 10 times 2 is 20, minus 1 is 19. 20 minus 1 is 19. 2 times 19 is 38, plus 0, 38. 2 times 38 is 76, plus 0, 76. Okay, so here this is now positive. So there must be a root between them. So that's all you have to do. So you can just note the sign change between these two. I like to show that with a little arrow here. You can see this, the sign changes. Okay, so there must be, so by the intermediate value theorem, which I'll label IVT, there is at least one real root between 1 and 2. We're done. Oh, I guess there could be, it doesn't have to be always an odd number. It could be also an even number. For example, if it crosses and then it touches, that's also a case where you can have two real roots between them. So you can actually have any positive integer number of roots between the two if there is sign change. If there's no sign change, then you're not guaranteed. There still might be roots between the 2 points. But if you don't get closer with your values of a and b, you can't know for sure. It doesn't tell you, just the information out here doesn't tell you what's happening here. So you need to go across the root, calculate the value of the function here, and then you know there's a root between those two. Like I say, the closer you can get to the root above and below, then the more accurate will be your guess of where the root is. Okay. And if you take calculus, you'll learn methods of calculating such roots very quickly. For example, there's a method invented by Isaac Newton called Newton's method, which uses derivatives and the slope and things to try to get a very accurate, quick estimate of the actual value of the root numerically. Okay. And you could also verify, you might want to find out for physical applications where the maxima, local maxima and local minima are, or global maxima, global minimum. Notice that if the function has an even degree, then there's always either a global maximum or a minimum. So there might be something like this if it's a quartic, and it shoots off to, say, negative infinity as x goes to plus or minus infinity. So that will have possibly local maximum minima, but overall an absolute maximum as well. Or it might have an absolute minimum as well as local maxima and minima. But a cube root or fifth power, whatever they look like, those will have no global maxima or minima because the endpoint behavior is to plus and minus infinity respectively at one or the other direction. It might be going like this as well. Okay, so in those cases you have no global maxima or minima, but you might have local ones. Okay, so all right, good. So now I wanted to continue with actually finding roots. Okay, so one problem, I'll just do it again even though it's done for you there. But it's page 403. It's an example of finding a root given one root of a polynomial, find the complete factorization of that polynomial. So some of these are cooked up problems, cooked up by me or the person who wrote the book. They're cooked up in such a way that the answers are not that hard. Generally speaking, the roots, it's difficult to find the roots of polynomials. They're going to be irrational numbers or complex values. But if you get it by multiplying together linear factors, which you know, you'll get an expression which it's really hard to tell whether it's easy or not. But in a course like this, usually we try to give you doable questions. Okay, so this one is such a question. So that's what I mean by cooked up. It's sort of prepared so that the answer is not that hard once you know the technique, once you know what you're doing. It's not too hard to find the answers. So show that. So this is a section we're continuing in section 5.5. Show that x plus 2 is a factor of x cubed minus 6x squared minus x plus 30. And also, I'll be giving you little techniques or tips, if you like, or little tricks, if you like, methods to make it easier to see what's going on. And some of these will be algebraic in nature. They might have to do with a synthetic division process. And there's something called Descartes' rule, which is useful for determining how many positive roots you might have or how many negative roots you might have. And it's really easy to find that out just by looking at the changes of sign of the polynomial in expanded form. All right, so now in this case, you're given that x plus 2 is a factor of this polynomial. Okay, so find the remaining factors and use the factors to determine the zeros of the polynomial. Okay, so and I hope you realize that, hopefully you know by now, that once you find the remaining factors of the polynomial, then the last part is really easy. You just have to equate each factor to 0, and that gives you the zeros of the polynomial. Okay. So how do we do that? All right, well, the first thing we can do is check that this is actually a factor of this polynomial by using the factor theorem. In other words, we use synthetic division. So we write down the coefficients of the polynomial. 1, minus 6, minus 1, and 30. Okay, so that's our first row. And then we put in minus 2. Okay, remember, I always change the sign of this part here. So it's actually the potential root of the polynomial. And then you evaluate, you do line division, usual way, and you get the remainder. And the remainder should be 0 here. But not only will you get to check that is 0, but you'll also find the coefficients of the quotient polynomial. That's why we want to do this, actually. Okay, so the quotient polynomial will be 1 degree less, namely a quadratic. And then we can always factor a quadratic using the quadratic equation to find the roots. So when we go ahead and do this, we bring down the 1, and then 1 minus times minus 2 is minus 2, plus minus 6 is minus 8. Right? And then 2 times 8 is 16, that's positive. Minus 1 is 15. 15 times minus 2 is minus 30, plus 30, well, that's 0. Okay, so that's good. So that means this is a factor. Minus 2 is a root of the entire polynomial, so this is a factor of the polynomial. And we found our terms, the coefficients for the quotient polynomial here. Okay, so you can start anew. You can write it down and do it the usual way, or you can actually use this. Right, you can factor this in the usual way, or you can use these this row to go ahead one more time and guess a root. All right, so you might have guessed already the roots are 3, and it's going to be minus 3 minus 5. Let's just do it this way. Put in the 3. So the root's going to be 3 and 5. So let's see what we get. 3 times 1 is 3, plus minus 8 is minus 5. 3 times minus 5, 15. Minus 15 plus 15 is 0. Okay, so that's giving us now the remaining coefficients, 1 and minus 5. And that's for just a linear polynomial. So the remaining factor is x minus 5. Okay, so after guessing the root, just by looking at what you do to factor, we get this expression. So you could do it the usual way. You get these factors, x minus 3, x plus x minus 5. And so all the roots, or the factors then are, put it all together, you get x plus 2 are the factors, and then the roots are minus 2, 3, and 5. Or all of the zeros as well. All right. Now, in looking for zeros, you want to have a way of guessing possible zeros for such equations. Now, in such an equation, such a polynomial, if you want to look for factors of this form, where the second constant terms are integers, notice what happens for these integers. If you have, the product of them must always be this last one here, 30. 3 times 5 is 15, times 2 is 30. And the minus signs cancel, so you get plus 30. Okay, so taking the products of all the constant terms gives you the constant here at the end. That's the only way to get a constant, is just if you take the product of the last terms here. The way to get the highest power is just take the product of the first terms in these factors. X cubed is what you get there. So that should have a factor of just 1 here. 1 times 1 times 1. So a reasonable thing to do to guess roots is you look at all the factors of 30. Okay, so what are all the factors of 30 here? Okay, well, factors of, if you factor 30 into its prime factors, that's a good place to start. It saves a lot of guessing, actually. So you factor into the prime factors. The prime numbers are 2. Remember what those are. They're 2, 3. 2 is the only even prime. 1 is not a prime. It doesn't count as a prime. It starts with 2, and then they're odd from there on. 3, 5, 7, not 9, 11, 13, skip 15, and then 17, 19, 23, etc. All right, so you can keep going. It gets harder and harder to calculate the primes as you go higher, but they've been calculated for you. Well, I don't know how high they've gotten as the largest prime so far, but it's a major effort to try to find the biggest known prime. Okay, so you look for the factors of 30. So you subsequently you divide by each factor in turn to see if it goes in, first of all. And you see the first 3 primes are actually what the prime factorization is of 30. Oops. 2 times 3 times 5. 2 times 3 is 6, and then times 5 is 30. So that's the prime factorization. This is always unique. There's no other way of representing 30 as a product of primes. And now you can construct all the possible factors. All the numbers which divide into 30 are going to be all the powers of these which are less than or equal to the power shown here. So here the power is 1 for each number. So the only other prime that's lower than that, which is still an integer, is 1. Okay, so I start with 1 times 1 times 1. That's one of the factors. And then I'll take 2 times 1 times 1. So I change only the power of 2, and then I get 2. Then I go, back to 1 for this. And then I change this to 3. And that gives me 3. And then I go 2 again. 2 times 3 times 1, which is 6. So you see what I'm doing is I'm changing this from 1 to 2 each time. And then I change this from 1 first, then it goes to 3. Now I'm going to go reset these back to 1, and then this will go to 5. And then this will become 2 times 1 times 5, which is 10. And this is 1 times 3 times 5, which is 15. And then finally I get 2 times 3 times 5, which is 30. Okay, so for each place, for each column, there are 2 choices. It's just 1 plus the power up here. Which is, so you multiply all those choices together, 2 times 2 times 2, and that gives you the number 8. So there are 8 possible factors of 30. One, 2, 3, 4, 5, 6, 7, 8. Okay, so doing this count in the same way. So what you do is you write 30, or you write the number as a prime factorization. Remember, 1 is not included as a prime number. It's not a prime, just by definition. And then you take each power and add 1 to it, and then you multiply all those together, and that gives you the possible number of factors. So 2 times 2 times 2 gives you 8. 8 possible factors of 30. Okay, so that's a I think it's a result from number theory. How to calculate all the factors of a given integer, of a given whole or natural number. Okay, so now once you have the factors of 30, you list all these. You list all the possible choices. Each of these could be a root. One, two, three, 5. I'll list them in increasing order. 6 plus or minus. So remember, we can have negatives as well. So each is positive, plus or minus. And then plus or minus 10, plus or minus 15, plus or minus 30. And that's 8 altogether, right? Okay, so that's a possible, these are the possible integer roots. And we're looking at any polynomial with ending in plus 30 like this. So it could have anything in there, but if it has integer roots, then it should be one of these, because it has to be a factor of 30. Okay. All right. So and then you would test them, and you would find the first one that works is minus 2, let's say, and then like we did, plus 3. Okay. All right. So let's try. So let's call the rationals now for rational zeros. It's called the rational zero theorem. We have to look at the factors of the coefficient in front of the leading, in the leading term. So in the general case, you have an an, xn, a leading coefficient, and a final constant coefficient, or constant, a0. So what you do is you list all the factors of a0, okay, and those you would give to the value p, and then you list all factors of an, and you call that q, and then you look at all the ratios p over q. All right. So these are the ratios which will be possible roots for this polynomial, and you just need to go through and check them all. Okay. Fortunately, they're usually a finite number, although there might be quite a few to check, so it might be a bit tedious. But in principle, those will give you all the possible rational roots. So the rational zeros. Okay. So let's try an example 3 in this section 5.3. List all the possible rational zeros of it's 2x to the 4th minus 5x cubed. Plus x squared minus 4. Yeah, this is 5.5. So we look at the possible values of p. So we have to look at the number 4. Okay, so 4 is 2 squared. So the number of different factors. By the way, the factors will always include 1. And the number itself. So if you write 4 as 2 squared, then you just take that power, add 1, 3, and there's nothing else to multiply it by, so that gives you the number of factors of 4. So there are 1, 2, and 4. It's easy enough to write them down. And you just put a plus and a minus in front of them, and that gives you all the values of p. And the values of 2, which we'll call possible values of q, which would come from the 2, and those will get plus or minus 1 and plus or minus 2. 2 is just 2 to the 1, and you just add 1 to that, and that gives you 2 possible positive factors. So the possible rational roots are, if I divide by plus or minus 1, I just get the same ones as here. And I don't have to repeat them, so try not to repeat them. If they're already there, you don't have to write it down again. I take 1 divided by 2, and that's plus or minus a half. And then it's 2 divided by 2 is just plus or minus 1. 4 divided by 2 is plus or minus 2. So I don't have to write those down, and that's all I have to write down. Okay, so now I tried all these roots, and it looks like there's none of these actually work for this polynomial. But if one could change the terms here, then it's possible to it might be possible that some of these are roots. Okay, so you might try it yourself and verify that has none of these are actually roots. So it has irrational roots then. If there are no rational, if these are the only rational roots it could have and none of them work, it means all the real roots are irrational. There is, I think there are a couple of, there are about, there are 2 irrational real roots, which you can find by looking at changes of sign. Okay, so I'll show you which sign changes I found. So let's see. So you write down these coefficients in the top row. Remember, there's an x term that's 0. The x term has a 0 for a coefficient there. So what I did was I tried 1 and I got 2 minus 3. I'll just go quickly through this. Minus, I made a mistake here. It should be minus 4, and then minus 8. So that's not a 0. And I tried going higher. 2, 4 is 1. Sorry, minus 1, and then minus 2 is minus 1, minus 2 is minus 2, minus 4 is again minus 8. And I tried going even higher. 2, 3 times 2 is 6, plus 1 plus 5 minus 5 is 1. 3 times 3 plus 1 is 4, 12, 36, 32. Okay, now in this situation, I'll make a note of this for you. If you see all the signs are now the same, and you've been going in increasing order, then try to increase this even more. We'll not change that. So what this means is there's no higher roots higher than 3. No real roots. So once you get all the signs are the same, then if you go higher, that will remain the same, and this will never become 0. So no real roots higher than, no real roots for x greater than 3. Now, the way it works for negative values of, going in the other direction, if you have 0, 2, minus 5. So when you plug in 0 and evaluate, you'll always just get the coefficients that you started with here. That's a useful thing. So I can just write down the coefficients. If I go to minus 1, I get 2 minus 2 minus 5 is minus 7. Plus 7 plus 1 is 8. Minus 8. And plus 8 is 4. Okay, so what's happening here is there was a sign change here. And so that means that actually I didn't even need to try this one. Yeah, because it's not a rational root, but anyway, I was looking for where the roots are. Because of this sign change, here, I know there must be a real root between 2 and 3 by the intermediate value theorem. And because of the sign change here from 0 going down to -1, again, I know there's a real root between those two values of x. So there's a root R1 and R2 such that -1 is less than R1 is less than 0, and such that 2 is less than R2 is less than 3. Okay. So that much I can conclude. I also tried the other rational roots, and nothing gave me a correct answer. -1/2 gave me, starting from there, 2. 2 times -2 is -1, -6. Half of that is 3 plus 1 is 4. Half of that is -2 plus 1, and then you see I got -3 there. So it doesn't give me 0. Finally, 1/2 gives me 2. 1 minus 5 is -4. That gives me -2 plus 1 is -1. And now I get a fractions the rest of the way here. -1/2 plus 0 is -1/2, and then -1/4, -4, so -4 1/4. All right, so it doesn't give me 0 here, so those cannot be roots. So I've exhausted all the possible roots. If I tried 4, it'll just give me something non-zero in the end. So I don't, because I can see that already from the fact that these are all the same signs. Okay. Now I checked where these roots are, and let me show you. So I graphed them using Maple. So let's just see it. So I'll switch over to the Maple picture here. So this is hopefully you can see that clear enough. Here's the graph of that function. So here you could see a root. It's really hard to see that, but this is just to show that this is a half mark and this is 1. So there's a root around here. It's about -0.8. So R1 turns out to be about -0.8. And R2 turns out to be around, it's up here, it's greater than 2, it's between 2 and 3, it's about 2.43 actually. So just getting that by approximation, this is about 0.80. Okay, so one can just verify that by using a computer or calculator, or even with a calculator you can estimate roots, and you can do these calculations with decimals and try to get the values between which there's this change of sign, get them to be closer and closer to each other, and that can allow you to pinpoint more accurately where the root is, what value it has to a few decimal places. Okay. So let's do another example. Example 4. Use the rational zero theorem to find all the zeros of the following polynomial. Okay, it is 2x cubed plus x squared minus 4x plus 1. Okay, so basically this one, it's pretty easy to look for, to find all the possible rational zeros. P can only be plus or minus 1. And Q can be either plus or minus 1 or plus or minus 2. So the rational roots P over Q can only be plus or minus 1. Divided by this doesn't change anything. Dividing this only gives you plus or minus 1/2. Okay, so let's just search through those possibilities. 2, 1, minus 4, and 1 are my coefficients. Now I look at 1, that gives me 2. 2 times 1 is 1, plus 2 is 3. 2 plus 1 is 3. 3 minus 1 is, minus 4 is minus 1, and then I get 0 here. Okay, so already we found a rational root. And our final polynomial is 2x squared plus 3x minus 1. So once you get the final result, if it is a quadratic, if you finally get a quadratic after taking this factor out, you know, if that's a quotient, then you don't even have to do this anymore. You could just use the quadratic formula to see what the rest of the roots are. And what I found was, using quadratic formula, b squared minus 4ac is 9 minus plus 2 times 4 is 8. So it's 17. That goes into the bracket. So you got minus 3 plus or minus square root of 17 divided by 2 times 2 is 4. Okay, so there are no, that's the only rational root was 1. But once you find that, then it's easy to find the rest using the quadratic formula. The irrational zeros are going to be, you know, have square roots in them. But you're asked for all the zeros, so just to list them all out, that's what you would get. Okay, so that's the only rational zero right there. Now find the rational, use the rational zero theorem to find rational zeros of, this is example, I didn't write it down, but it might be a try it question, so. Anyway, so this other example, use your rational zero theorem to find the rational zeros of f of x is equal to, I have x cubed minus 5x squared plus 2x plus 1. Okay, well, yeah, I think this was one of the try it questions. Try it. Maybe, I forget which one, number 3 maybe? Okay. So you see right away the p can only be plus or minus 1. The q can only be plus or minus 1. And so that means p over q can only be plus or minus 1. Well, those are the only possible rational roots. Okay. Rational roots must always be, yeah, you can read about it in the book. It explains a little bit more by an example, but the numerator must always be a factor from here, and the denominator must always be a factor from this coefficient here. Right. Assuming these are all integers in between as coefficients. So what you do is you just try out these two possible factors. And these are the coefficients that you would use in synthetic division. So you try 1, carry down the 1, and you get 1 times 1 is 1, minus 5 is minus 4. minus 4 plus 2 minus 2. Minus 2 plus 1 is minus 1. Or you try minus, so that's not 0, so that's not a root. Then you try minus 1, and you get 1 times minus 1, and plus 1 minus 5 is minus 6. Plus 6 plus 2, 8. Minus 8 plus 1 is minus 7. So again, not equal to 0. Okay, so those are neither of those are roots. And so, since those were the only possibility for rational roots, the only possibilities, that means you've just shown there are no rational roots. Okay, so now, by the way, a tip. Here, this illustrates this tip. It might be a good idea when you're looking at the coefficients, check to see if they add up to 0. If they do, in this case they do, 2 plus 1 is 4, minus 4 is 0. Okay, so if they do, which is right in this case, then the root will be simply 1. The root 1 will be a root of this polynomial. Because that's what you do when you do synthetic division there. You end up adding up, 1 times 2 stays the same, and then you add it to this coefficient. And then you add that to this coefficient without changing that. So you accumulate the sum of all the coefficients. So as a result of 0, that means the evaluation of the synthetic division, using that as the initial starting value for x, must be 0, and so that's 1 is then a 0 for that polynomial. Okay. So that's sort of a trick that another trick that is helpful. So another tip. Coefficients is 0, then x equals 1 is a root. There's another tip. Let's, while we're at it, give you another one. If the alternating sum of the coefficients, so if you change the sign of all the odd terms, let's say, the coefficients of the odd terms change sign, and then the coefficients add up to 0. Okay. The alternating sum of the coefficients is 0. You just change the signs of the odd coefficients, of the coefficients of the odd terms, in other words, the odd powers of x, then what's going to be a root there? Minus 1 is going to be a root. Okay? Because that's what you do when you evaluate minus 1. You change the sign every time before you add it to the next coefficient. So just changing the signs of the odd powers and then adding. Then that will give you the result of the evaluation. If the result of the evaluation is 0, then that means minus 1 is a root. Okay. And I gave you tips about it when the numbers when they're all alternating. So here you can see they're all alternating signs. So if you go any lower, there cannot be any more roots at all. whether they're rational or not. And we have yet to see if there's a sign change. Eventually there's going to have to be a sign change to the positive, because this is the end behavior. This is going off to plus infinity. So there will be a real root as you go higher, but it will not be a rational root. Okay, it won't be a rational zero here. Okay, so well, let's see where it does change sign. So we have to go bigger than 1. Oh, that's actually this is if we go through 0. Sorry, yeah, that's going to be this row. And that's already positive. So there's a change in sign from -1 to 0. So there's a root. And then from 0 to 1, another change in sign. So there's a second root. Okay, so now there's going to be a third root as well, because I'll have to have another change of sign in order to get all positives. So let's try 2. 2 times 1 is 2. Minus 5 is minus 3. And then 2 times minus 3 is minus 6. Plus 2 is minus 4. Minus 8 plus 1 is minus 7. That's still negative. I'll have to skip up a little bit to get a positive. So 3 will give me still minus 2 here. 4 will give me minus 1. 5 will give me 0. And then I'll get 2, 10 is 11. This is going to be good enough. And then if I go higher, you'll see they'll all be positive, and they'll remain positive afterwards. So this will be plus 1, this will be 8, this will be 648, 49. And so there's a sign change from here to here, probably between, well, I don't know exactly where, but not equal to 5. But after that, there's no more possibility of roots, because it stays positive. Okay, so that gives me all the locations roughly of where the 3 roots are. They're all going to be irrational, but they're all going to be real. You have to find them by approximate methods. Okay. Let's just, well, while we have Maple here, it might be handy to just check to see what happens there. So I'll just go over to my other scene, and I'll show you what I do here. So I type in, I'm showing you a third possible polynomial. I'll get back to that when I get to that. But so let's go to our case here. So I'll plot this function x cubed minus 5x squared. Oops. Press the wrong one. Minus 5x squared plus 2x plus 1. And I'll take x to be going between, I think the lowest root was between 0 and minus 1, right? So that's going to be minus 1 is the lowest, and up to 5, let's say. It should change by 5. Okay, so you see what's going on then? Try to make this bigger. Okay. So hopefully you can see that. So it's showing you that between 0 and minus 1 there's a root. It's close to about negative 0.25 or something, or negative 0.3. And then there's a root at about it's going to be about 8, 0.8, so it's between 0 and 1. So just as I showed you before, right, those are where I indicated there are two sign changes. It goes from -1 to 0, there's a sign change, and then 0 to 1, there's a sign change, and then over to 2. So I didn't do this in exactly the right order. But then the final root is between, you can see it's between, way up here, between 4 and 5. Yeah, so it does change sign finally up there. Okay. So let's just check this out. I'm just going to plug in my computer since I left it off with the power for a while. Forgot to plug it in. All right. Okay, so now you can see how it's possible to verify this using some technology. I can send you this also by email this to you. And anyway, so we'll get back to some more examples. Descartes' rule of sign. Oh yeah. Okay. So this is a tip or trick or little helpful thing. Descartes' rule of signs. I keep on saying it the wrong way. French is Descartes. The pronunciation is yes. Descartes was the person who invented the Cartesian coordinate system. So he made he helped to make this very strong connection between algebra and geometry. Okay, so what this rule says is that you look at a polynomial written in expanded form, and you look at the changes in sign. So you write it in decreasing order of powers of x. Starting with the largest power here, decreasing as you go from left to right. Okay, and you count the number of changes of sign. All right, the 0 doesn't count at all. So if there's a 0 coefficient, then you don't have to count that. All right, it doesn't count as a change in sign, in other words. Let's go from positive to negative, or from negative to positive. So here there's one change in sign. So what that means is that there is one real 0, real positive 0. This is a positive. If I tell you it's positive, then you know it's real. Okay, so there was one real 0, x, such that x is greater than 0. Okay. So there's one change in sign. Then you look to find how many negative zeros you have. You replace x by minus x, so that changes the sign of just the odd terms, the terms which are odd powers of x. Then you count the changes in sign. You get one here and another one here. Okay, so there are two changes of sign. Okay. Now what that means is that there are either 2 or 0 negative roots. Okay, so however many changes in sign, in general, you just count the number of changes in sign, and And the number of positive roots of, if you start with the original polynomial and you do that, the number of positive roots will be that number or any multiple of 2 less than that. Whereas if you want to find the possible number of negative roots, then you replace x by minus x and you get another polynomial. Again, you count the changes in sign. And again, it will be, that number will give you the number of negative roots, or the number of negative roots might be 2 less than that, or it might be 2 less than that, and so on. And you go all the way down to 0, or 1 if it's an odd number. Okay, so if the number of changes of sign are 0 or 1, then there's only one possible situation, whether it be positive or negative. You only have 0 or 1 changes of sign. But if it's 2 or greater, then you have multiple choices of how many roots it has that are positive or negative. Okay, so let's see how that works. For these different cases here, for some examples. So for this one, let's find the rational zeros, or the possible rational zeros. Okay, so P can be plus or minus 1. Q can be plus or minus 1, plus or minus 2, plus or minus 4. So the rational roots could be plus or minus 1, plus or minus 1 over 2, plus or minus 1 over 4. Okay, let's try it out then. So 4, 0, let's search for the roots by using synthetic division. So let's try 1. So I plug it in. Okay, by now, if you're trying to practice the tips that I've been giving, adding up the coefficients gives you 0. So already some of you might have guessed that 1 must be a root. So let's try it. 1 times 4 is 4, plus 0 is 4, plus 3 is 1, plus 1, and then minus 1 is 0. So already we get that 1 is a root. Okay, what else are roots? Well, if we look at the remaining coefficients and put it back, we get a quadratic equation. And this you can recognize as a perfect square, namely 2x plus 1 squared. Because if you take half of the middle coefficient and square it, and this coefficient is 1, then this must be this is the same as 2 squared. So the remaining roots are minus a half, they're repeated. These are all the roots. This is multiplicity 2. Okay, well did Descartes' rule actually predict that correctly? Yes, there is one positive root. And for here we have 2 negative roots, yes. So this is what it turned out to be. Okay. All right, and what does the graph look like? Well, since we have a repeated root, the factored polynomial will be 2x plus 1 squared. So that's a repeated root, and then x minus 1. So what it will look like is it will pass through x plus 1. It will have a positive coefficient, so have a positive slope. It will go off to infinity as x goes to infinity because it's a cubic with a positive factor in front. And at x equals minus a half, it has a negative. If you plug in x equals minus a half here, you get a negative coefficient, so it's a quadratic or a parabola which just touches from below. What's the y-intercept? That's a good thing to calculate. So f0 is -1. So it intersects somewhere here along the negative x-axis. And then it does something there. And here that goes off to -infinity. All right, so just using these features, graphing it, gives you a picture of that's consistent with the fact that the roots are what we showed they are here. -1/2 repeated twice, and then 1. It's multiplicity 1. Find the zeros of the polynomial function with complex zeros. All right, so this is example 6. We have f of x is equal to 3x cubed plus 9x squared plus x plus 3. Okay, so how do we do that? Well, the book does it differently, but I could see that it's, I noticed, I should say after I did it the hard way probably, that you could do this by grouping. So if you group this factor and take out the largest denominator, or common part, it's 3x squared, then you're left with x plus 3. And here you get just 1 taken outside gives you the same factor left over, x plus 3. So you combine them, you get x squared, 3x squared plus 1 times x plus 3. Okay, so another way to do this, which I think is what the book does, is you look for all the possible rational roots, and they're plus or minus 1, plus or minus 3, plus or minus 1/3. And you try them all out, and you get, when you hit -3, then it gives you a root, and you can factor it. Okay, so yeah, if we did it that way, let's see what would happen. So again, we would try it with 1, and that gives us 12. Actually, we can see right away it's going to add up and give something non-zero. Right? Descartes' rule of sign says no positive roots at all. Okay, so 1 times 3 plus 9 is 12, plus 1 is 13, plus 3 is 16, so not a root. 0 is just what you get for the first row. 2, so not a root. 2 won't give you a root because it's still even more positive, so let's go negative. So if you look at the negative, if you change the signs of the odd terms, then you get negative 3x cubed, right? Minus 3x cubed plus 9x squared minus x plus 3. So those are 1, 2, 3 changes of sign. So we could have 3 negative roots or 1 negative root. If you always go down by multiples of 2. Okay, so if we try -1, that's our only other option for a negative root besides plus or minus 3, or -3 and -1/3. Let's try those. Okay, so -1 gives us 3. Minus 3 plus 9 is 6. Minus 5, and minus plus 8. So that's not a root. Right, so the alternating sum does not vanish. We get 12 minus 4, yeah, I'd say that's correct. So then we try 3. 3 doesn't work because it's got to be negative, right? So negative 3 instead. 3 times 3 is -9, plus 9 is 0. Times 0 is 0, plus 1, 1. 3, or sorry, -3 plus 3, again 0. Okay, there I get a root. So that gives me the factorization here. 3x squared plus 1. And that's when I noticed, well, you can do this by, you can do this by grouping. Okay, are there any other real roots? The answer is, that's one real root. Can you get real roots from here? The answer is no, because you cannot solve that equation and get real values. You have to get, when you solve that, you get complex values, namely x squared is minus 1/3, so the roots are plus or minus I over root 3. So you have only one negative root. So Descartes' rule was right again. Okay. And that's so all the real all the zeros of the polynomial are minus 3 plus or minus I, and I should put it in the form where the denominator is rational. Plus or minus I over 3 root 3. Those are all the roots. Complex ones included. Okay. Try number 4. Okay, so lots of stuff to do here. Actually, I'm probably getting close to a good time to stop, since I've been going for about an hour and a half. So the rest is, so I would advise you could just go on ahead by simply doing the try-it questions, doing the examples first. Actually, it might even help to cover over the answer and try the examples on your own before looking at the answer, before peeking at the answer. That's always a helpful way to kind of accelerate your understanding. You have to think through everything. You can think through things in your own way. You don't have to necessarily do it the book's way, but if you get it correct, usually it's an encouraging sign that you know how to figure stuff out like that. So usually it's just using the logic that you learned in the textbook to apply to a problem, and trying out the different things you just learned. Okay, so the next one I was going to do was try it number 4. Find the zeros of a polynomial 2x cubed plus 5x squared minus 11x plus 4. I just tested out all the rational zeros. Okay, here's some examples which are of different character. This is using what they call the complex conjugate theorem. I didn't call it by that name, but I essentially said the same thing. Complex conjugate theorem says that all the complex roots come in conjugate pairs, complex conjugate pairs. Okay, so that was just the complex conjugate. Here. So, example 7 was a particular example. It said to find a fourth. So you could just see what that says. The triad problem was a similar one. Try it number 3. Okay, I might be getting into section 5.6 at this point. Because the triad note is all now a smaller number. So triad number 3, you're given that 5 is a root. You're given that 2i is a root, and that f of 1 is 10. And the polynomial is degree 3. Find the actual polynomial. Okay, so if you know what the roots are, and you know the complex conjugate theorem tells you there are 2 complex roots, not just this one, then you can easily figure out the third root. So the first two roots are minus, so you put in a factor of x minus 5, that indicates the one root, or it will represent this root, and then x minus 2i. So the other factor has to be x plus 2i. Oh, you're given that the coefficients are real. Coefficients of the polynomial are real. So that's what's necessary for the polynomials. What I'm trying to say is that what you need for the complex conjugate theorem to work, to be true, is that all the coefficients of the polynomial have to be real, and then the roots come in complex conjugate pairs. So you have this. This is the going to be the form of the polynomial times a factor a, which you don't know. But this is the other real or complex root that you have to have, the conjugate of this, minus 2i. And then you're given f of 1 is 10, so that allows you to evaluate a. You just stick in x equals 1 everywhere, so you get minus 4. And this whole thing together is x squared plus 4. And you take that, evaluate that at 1, and that's going to give you 5. So minus 20a. And so a must be minus a half. Okay, something. Maybe I did it wrong in my book, but I think this looks like it should be correct. So f of x is minus a half x minus 5 x squared plus 4. Okay, 1, if I plug it in, I get 5 minus 4. Yeah, looks like it's correct. Okay. So to get prepared more explicitly, next time I want to do some of the problems in the back, and I'll just list some of the ones I did. So if you want to try them, go ahead, and then I'll just give this. Try them before next time. See if you can do that, and then at least I'll give you this one. It's kind of a hard one. Okay, to prepare for that one, let me give you a few more which are a bit easier. So I'm on the exercises in 5.5. Yeah, so I think we're still in 5.5 here. Sorry. The exercises I tried were number 6, number 11, number 21, number 22, and then this one, which is quite a difficult one. But go ahead and give them a try, and yeah, in this number 39, you get a polynomial which you have to look for the rational zeros for it. But just to give you, just to encourage you, there are 2 rational zeros for it. You just have to look for them a little bit. Spend some time to do that. Make sure you find them. So they're not the easiest ones, let's say. And then once you do that, then you can factorize. You can find all the roots, and there are complex roots as well. Okay, so I'll just stop there, and let's just continue next time, and I'll work on a few of these other problems. You might also try the bakery problem, which is mentioned at the beginning of the chapter of this section, and it's finished at the end. So you can read that in the textbook as well. Okay, so with that, I bid you adieu, and have a good night, or whenever you're watching this. So, Godofus. Take care.